Alright, this is the sample test for Unit 4, exponential and logarithmic functions. Problem number 1 is sort of a word problem, but really it just boils down to we have an exponential equation, an exponential function, where the function is for the world population. So f of x represents the world population in billions, and x is the number of years after the year 2000. How many years it's been since 2000. And so it really just boils down to like an evaluation type thing. We're evaluating a function because they go on to give you a year. So for the year 2030, that would make x what? Remember, x is not the year, it's the number of years after the year 2000. And so all we're going to do is plug what in for x? Well, spoiler alert, 30. We're going to plug 30 in for x, and then just let our calculator tell us, what that's going to equal as far as the population, the overall population. And just want to make sure certain calculators minimize the risk of, punching something in wrong. But on certain calculators, you might have to just really make sure that the calculator knows that all of this is going to be the exponent. So sometimes you have to make sure to enclose all of that in parentheses. You might be safe on this particular problem no matter what, but can't hurt to be too careful, right? Here. Okay. So anyway, what was your calculator say? Make sure that you can, make sure you're comfortable plugging all that in, and it looks like this is approximately 13.034 billion peoples. Okay? So just plugging in, chugging problem. Number 2 wants you to graph an exponential function, and to do that we're essentially going to make a table. Remember, if you're just listing a bunch of points, that's essentially the same as making a table. A table is essentially a list of XY pairs. So identify the points. Use at least 5 points. So you're probably plugging in x values such as 0. Maybe we'll do it this way. You're probably plugging in 0. You're probably plugging in x values like 1. It's definitely crucial and always smart to also plug in negative values. I mean, really, I've probably said this in class once or twice. Oops, spoiler alert. No, maybe not so much. Anyway, as I was saying, I've probably said in class once or twice or whatever that when you're trying to just kind of throw together sort of like the sketch of a graph by making a table of points and just plotting a handful of points and using those points to figure out what the graph is going to look like overall. How do we connect the points and the dots then? But really, anyway, the more points you come up with, the better, If you only come up with like 2 or 3 points, unless your graph is a line, right? If it was a line, that'd be fine. But for most graphs, just like 2 or 3 points is not going to give you a clear enough picture of what the whole graph is going to look like. You know what I mean? So the more points you have, the more your graph, becomes clear and takes shape. You know what I mean? So anyway, it might be better to throw in points like -5 or positive 6. You know what I mean? Kind of like a wide range of points and maybe numerous points, but I'm just asking for 5 of them here. If you were to plug in 3, you'd get, wait, what the heck's going on here? If you plug in 3, did I accidentally... Ooh, something's weird going on. A decimal point probably got moved or something. This is embarrassing. Let's just do this again. So 1/3 all to the 3rd power. So if I'm plugging in 3, I'm going to get, grab my pen, get the right color. Okay. And it's supposed to be a decimal point right there. I'm sure it was there at some point, but maybe I accidentally hit an undo button or something, or whatever. All kinds of things happen with this active Inspire, software. Weird things. So there should be a decimal point right there. So 3, 0.037 and -3, that's correct. But if you plug in 0, what happens if you plug in 0 in for x? The function's going to equal 1. If you plug in 1, you get about 0.33. If you plug in -1, you get 3. If you plug in -2, you get 9. If you plug in +2, you get approximately 0.11. So plotting all these points, and I probably plotted some extra ones, but here are your dots. And hold on, make sure that don't just move on to the next problem before you hear me say that. These points on your test, you're gonna need to connect them, because the entire graph is not just the 5 points you happen to randomly plot, So, yeah. Oh my gosh. And so look, for this graph, as you take your x values more and more to the left, like as you plug in, look, -1, then plug in -2, plug in -3, plug in -4, and then you think even more like plugging in -10 or even like -500, whatever. It looks like these dots are just going to skyrocket high for the y coordinates. But what's going to happen over here? I mean, as I was plugging in 1, this is what I got. So, 0.33, If you plug in 2, you get 0.11, right? If you plug in 3, man. And then what's going to happen as you plug in 4, and then plug in 5, and then plug in 6? What's going to happen if you keep going way to the right, plug in 1,000 for x, or 5 million? What's happening is it's going to get really small, but never actually hit 0. So that's why we have this horizontal asymptote that you need to include on your graph. Oop, that was a little too, it's weird to try to draw accurately, but your arrow, your graph, the end behavior, right, just kind of keeps on creeping closer and closer and closer and closer to the x-axis forever. So make sure to include that dashed horizontal line representing the horizontal asymptote. All right, now these are getting probably a little simpler and more one-dimensional kind of thing, like just one step kind of stuff. So we're going to go a lot quicker, I guess. So here we go. Number 3 wants you to change something that's in log form, and you want to change it to exponential form. And so here's how we do that. Just a quick little review. Log form, when something's in log form, logs have a base, and obviously exponents in exponential form also have a base. The good news is the base in this form is going to still be the base in exponential form. Okay? And if you also remember that logs are really just exponents, so where this log, this entire log, is equal to 6, that makes 6 an exponent. And if 3 is the base and 6 is the exponent, we have 3 to the 6th power. And the other piece of the puzzle, x, that's what 3 to the 6th power is going to equal. And if you notice, here's even like, I mean, just for me to be like a little extra, almost like unnecessarily thorough, I could remind you that in log form, my x was my input, and down here it's kind of like x is my output. And up here it was almost like 6 was my output, but here it's more like 6 is more your input. So that's how you pretty much change log form to exponential form. Base, base, power, because that's what the log equals, power. And then the third piece of the puzzle is just the only leftover thing to put in its spot. Going the other direction, changing exponential form to log form, it's just very simple matter of just doing that in reverse. Here, x is the base, and so x is going to be the base of the log, right? There it is. And if 4 is my power, then that's what the entire log is going to have to be equal to. And then 16 just goes in the leftover place. And again, here 16 is like my output. It makes sense that here 16 is more like my input. Remember, because inverse functions are about input becoming output and output becoming input. The big switcheroo. Oh man, we're cruising. 5A. Question 5, it starts to be about just evaluating the log. You know what I mean? So like, what is the log of 8 base 2 equal to? In other words, you ready? Here's a reminder. This is essentially asking you 2, which is a base, 2 to what power would get you 8? Remember, logs are exponents. So 2 to what exponent would get you 8? I hope you're comfortable enough with all different kinds of powers to just know that it's 3. If you need to play around in your calculator, do a little guessing and checking, I mean, whatever, you got to do what you got to do. But the answer's just 3, people. 2 to the 3rd power equals 8. It's kind of vital to know that ln represents a natural log. And people, I mean, what defining characteristic makes a natural log a natural log? And I hope this isn't something you're still shaky with, but a natural log is simply a log that has a certain base. It's not written out in the open, just by seeing the whole ln notation. You need to know that the base is e. So it's almost like you could see an e written there, but you're not, but it's there. The base is e. So this question's like asking you, e to what power gets you e to the 4th power, It's almost so simple, it's tricky. You know what I mean? E to what power is e to the 4th power? Well, I hope by now you're totally comfortable with the answer. Should be 4. E to the 4th power equals e to the 4th power. So, yep, that's how that one works. And all right, man, we're already moving on to, this was section 3, most likely. It's in 2018 it is. So in section 3, we started talking about the properties. Got to know these properties forwards and backwards. I don't think you're going to have a cheat sheet or access to notes or anything. So you have to know about the product rule. You have to know about for some reason I feel like writing these down. The product rule. You have to know about the quotient rule. And you also have to know about the power rule. Okay? And when the directions say expand, that means that you're applying these properties from left to right, so to speak, like as the properties are written. You know, I guess you're applying them in like the forward direction. I don't know. I hope I'm making sense right now. But you're using the properties. Again, I don't know how else to say it. Like from left to right, you know, you're using them to expand. You know, like if you know the product rule, which you should at this point. The product rule is about taking a single log of a product and expanding it into a couple of logs that are added together. Of course, you could use the same property to condense two logs together, but whatever. So that's what I mean, I guess, when I'm saying like when we're expanding, we're kind of applying the properties from left to right instead of right to left. Anyway, here we go. As I just already spoiled a little bit a few seconds ago. This is a single log of a product, and so we're going to apply the product rule first, okay? Not to be overly thorough here. Is that even possible? I think I really should say that. If you're looking and going, oh, there's a power, I can bring the power down. You really shouldn't. Like, that would actually be wrong. Because this 3, the power of 3, only applies to the x. That power of 3 does not apply to the entire 36x. And so we actually need to break it up into a couple of logs. And so now, sorry, I just heard screaming in the hallway. When this 3 is now only with the x, like we've isolated x to the third power in its own log, now we can bring the 3 down, okay? Now we can bring it down, which we will, in a second. But the directions also say, where possible, evaluate, cleanly any log expressions you can, which if you look at this log, I hope you're keeping an eye out, and I hope you notice this without any problems. The log of 36 base 6, that's a very clean answer. Like 6 to what power is 36? 2, So 2 plus, and then what did we still have to do here? We still needed to apply the power rule from left to right, which means like bringing the power down in front. And that would be our final answer. Number 7, more than anything, is remember, you should be trying these before cheating through the video, right? But so, just cutting right to the chase here. More than anything, this is a log of a quotient, okay? You might already see the power that's involved, you know what I mean? But you're not going to bring that power down until you apply the quotient rule. And, well, look, see what I did already? The square root of x. You absolutely need to think of it not so much as the square root of x, but x to the 1/2 power. Because if there's a power, involved, which means we have the door open to use the power rule, that's what we got to do. But, you got to do the quotient rule here before we bring the power down with the power rule. And is this a clean log that we can evaluate? 4 to what power is 64? Yep. And so in the final answer, we have to bring the power rule well, we got to use the power rule, bring the 1/2 down. And the log of 64 base 4 is just 3. And then that one's done. Number 8. See, now we're sort of changing gears, or we're into the reverse gear. And, haha, I get it. And we're going to use the properties to condense. Or, like I might have said, like smush logs back together. And put things back up into the power spot. But anyway, number 8 is the log of something plus the log of something. And since there's no special coefficients, other than 1, of course, out in front, like we can apply, like the product rule applies. If there was a 5 out in front or a 2 out in front, the product rule would not actually apply yet. But here we're good to go on the product rule, and we can smush these logs into one log, or condense the logs into one log, and that's going to be, the log of a product. It's the product rule. And so the final answer, which you're probably going to want to have, is the log of 21 base b. And that's done. No other properties to apply. Number 9, see what I was saying? You have a log minus a log. I know it's a natural log, but you have a log minus a log. Does the quotient rule apply? Well, technically not yet. No. Because there's this 3 out in front, okay? Like that is not what the quotient rule says. So what you need to do first is actually apply the power rule. By putting that power back up as a power, we're putting that 3 back up as a power, and now we can apply the quotient rule to this. Now the quotient rule applies, and your final answer, again, hey, it's a log minus a log, natural log minus a natural log. When it condenses together, it's 1 log of the whole quotient. That's exactly how it needs to be written. If you want to put parentheses around the fraction, that's fine. But this is the final answer. X cubed over y here, 1 single natural log. Now we're into section 4, which was solving equations. And remember, with exponential equations, what you're looking to do ASAP is take the natural log of both sides, which will allow you to be able to use the power rule of logs, logs, to bring the power down. So are we able to do that right away? Would it work out? Like if I had the natural log of both sides, would I be able to apply the power rule? Yeah. Yep. And so we can go ahead. Ooh, I did 2 things at once, just kind of heads up. When you take the natural log of both sides, so maybe I'll do this just to make it seem a little more. If you take the natural log of both sides first, then you can bring down the 4x minus 2. But make sure, gang, that you put it in a set of parentheses. Put it in a bubble. All right? Because we're not just going to be having the negative 2 in front of the natural log of 2. It's this whole 4x minus 2 in a bubble, in a grouping. And after you do this, like once you're able to pull the trigger on that whole power rule trick, now it's just about solving for x. Okay? Now it's just about solving for x. Now what I would do next, you don't have to, I mean there's other paths to take, eventually getting x by itself the old-fashioned way. But I like to clear bubbles and by using the distributive property. So what I did was I distributed the natural log of 2 to get this. And what I'm going to do next is just continue to isolate and work on getting this x all by itself. So I think I'm going to add 2 natural log of 2 to both sides to get this out of there. And then what I have here is 4x natural log of 2. And since this is all being multiplied together, I can pretty much divide by the 4 and the natural log of 2, like at the same time. Essentially, divide both sides by 4 natural log of 2, and that'll get rid of the 4 and the natural log of 2, like at the same time. And that'll get x by itself, and be done with that. So anyway, so here's what we have. What do I have over here? Oh, cheeky. Anyway, bottom line is, you could take this as like an answer, and you would now be ready to like get your approximated answer. And so you would just have to throw all this into a calculator, making sure, you know, it depends on what calculator modes and what calculator you're using, but you might need to enclose the entire numerator in its own set of parentheses. Okay? And also, you know, even when it's not necessary, you might want to just do this all the time. I think here it might be necessary. Anyway, but always do it. Enclose your entire denominator in parentheses. Okay? But when you do that, what's your calculator going to say? It's weird. Your calculator is just going to say 2. You know what that means? That means you could have done something fairly clever from the get-go. Okay? I don't want to emphasize this too much because on the test, this special strategy might not even apply. All right, I'm just saying. But if in certain problems, if you notice, like with the bases 2 and 64, if you see an opportunity to just go, wait a minute, 2 to the 6th power would get me equal to 64. So this 4x minus 2 must just be equal to 6, because again, 2 to the 6th power equals 64. So you can pretty much just kind of do it a different way and just set 4x minus 2 equal to the power of 6 and just solve for x and you're going to get 2. But anyway, I tend to more emphasize this technique because it's always going to work, and if you're going to your calculator anyway to approximate an answer, your calculator knows that all of this is just equal to 2. Like, you're not even approximating here, it's just 2. The answer is 2. But in number 11, you will have to approximate, it looks like. 5 to what power is going to equal to 13? Anyway, so what you're going to do here is, you know, am I ready to take the natural log of both sides from the get-go? Would the power rule then apply? Yep. And once again, let me, you know, take the natural log of both sides, because then and only then would you technically be allowed to bring the x down via the power rule. And then what would you do from here to get x by itself? Because again, in that basic 3-step strategy, or whatever you want to describe it as, you know, after you're able to apply the power rule, now it's just a matter of get x by itself, you know, solve for x however you need, by whatever you need to do. And here, all you would need to do is divide both sides by the natural log of 5. And your calculator will say that, you know, you'll just have to approximate it to 3 decimal places. Okay? Before I move on to number 12, actually, let me, I'll move on and then say it, you know. So, moving on to number 12, if you were to, I just want to make sure you heard this right. So, if you were to go with just like a regular log of both sides And by regular log, I mean like log base 10, you know. Just like your generic log, which is going to be base 10, you know. Your calculator has a natural log button capability, and it also has a log base 10 capability. Like that's the typical log log button, right? Anyway, if you would have taken a log of both sides, you know, that would have worked too, because then your final answer here would have been log of 13 over the log of 5, which will also get you this answer, you know. And again, I've said this in class, unless you were missing that day, or unless I strangely forgot to point this out, you know, in all those classes. But I probably did, like 99% likely that I pointed this out in class, if you were there. So, you know, remember, we just take the natural log of both sides, you know, because if there happens to be an e involved in the equation, then taking the natural log of both sides, like, potentially can really pay off, you know. Anyway, number 12, would we be able to go ahead and take the natural log of both sides right away? Yep. And so you take the natural log of, again, like, just make sure it's like we take the natural log of both sides, then we bring the powers down, make sure you put them in parentheses and groupings, and from here, and again, now it's just a matter of how the heck are we going to get x solved for now. Like, once we bring it down, we can definitely, it's a whole lot more doable to solve for x. So what I would do next is distribute double dose. I clicked on the pen. A double dose of distributing, and that's how I get to here, x natural log of 3 plus 4 natural log of 3 equals 2x natural log of 7 minus 1 natural log of 7, or just natural log of 7. Now what we do, to remind you of this basic process, I mean, what would I do to get x by itself, you know, solve for? I'm going to move this term to the left side, so the x terms are together, and I'm going to move this term to the right side in order to kind of separate the terms that have an x, separate those from the terms that do not have an x. So I'm going to get the left side terms with an x and the right side without. Because what I'm going to do next, now that I have a term over here with two terms, and they both have an x in common, I can factor an x out as a greatest common factor, or a common factor is really what matters. I just want to bring out the x. I want to factor out an x like you would do like a GCF. And then whatever's left over here in the bubble, I'm just going to divide to both sides in order to leave x all by itself and solve for. Okay? And so the right side becomes, let me get a different color here, purple. Go Donatello. The most valuable of all the Ninja Turtles. You'll never convince me otherwise. Anyway, so this whole thing over here is what x, you know, because you're going to like, you know, because all this is going to be gone, can't, you know, and x will be by itself equal to all of this. And so again, if you were to throw all of that into your calculator at one time, just make sure you're putting, especially with some calculators, put the entire numerator in parentheses and the entire denominator in its own set of parentheses. And not to mention, maybe I should have said this even earlier, I think I said it in class most likely, but you know, the natural log of 7, you have to like close the 7, because most calculators will automatically give you a left parenthesis after typing in ln. Same over here. So with this 3, it's like there's going to be a 2 right parentheses in a row. Same thing down here on your calculator screen. 2 right parentheses in a row. Anyway, make sure you're able to type this in, like literally go through the motions of typing all this in to make sure you're able to have your calculator get about 2.270. 2.270. Number 13. Now, okay, we're changing gears, I guess, because now it's about solving log equations. And your basic strategy for solving log equations is isolate the log if you have to, and then convert to exponential form. So the way number 13 is right from the start, can we convert that? Yeah, we can convert that. There's no extra work needed at the beginning, so let's convert this just like we did earlier in this test, in the sample test. And so 4 is the base, 3 is the exponent, and it's going to equal, I know that looks like a big old thing, a bubble, but yeah, whatever, who cares? 4 to the third equals 3x minus 5. And now, like, see how solvable this just became when you think about now just getting x by itself and solving for x, right? Okay. Didn't think I needed, well, all I really did was 4 to the third is 64. Now you're going to add 5 to both sides like you've done a million times and divide both sides by 3. Oh, yep, that was the Women in Engineering field trip, which probably ended up on Facebook in 2018. Anyway, so where was I? So we're just dividing both sides by 3. And yeah, so I still have to email those pictures to the guidance counselors to put on Facebook, I guess. So easy answer, nice clean answer of 23. Number 4. Oh, okay. So here we finally are in a situation where we can't really do that money step just yet. And what we have to do, see, like, can we convert this as is? No. We have to like isolate the log part, this natural log of 2x. So the first thing we have to do in this situation is subtract 3 away from the left side. So it becomes 12. And then I still can't convert this, not with the 4 out in front. This is not written in a way where you can convert it, So we also have to like divide both sides by 4 and get the 4 out of there. And so the right side becomes 3. Now we can convert to exponential form. What's the base? The base is, of course, e. So e to the third power equals 2x. That's the money step. That's the money step. And now, oh my gosh, now we just have to divide both sides by 2. Remember, the ultimate goal is to solve for x, get x by itself. This would be like an exact answer, but name of the game here is to approximate. So just go in your calculator and do e to the third power divided by 2, and that's what you should get. Final question, a very doable bonus question. One of the biggest gifts as far as bonus questions I've probably given all semester. So in this bonus question, obviously we can't convert this to exponential form when there's 2 logs. So the first move here is smush them together by using the product rule, that property. And so we get to here, and now we can convert. Base is 2, 4 is an exponent, so 2 to the 4th, jeez. Wow, okay, hold on. I think there's at least 2 things happening at once. So 2 to the, wait a second. Okay. Phew. I didn't even convert this yet. Wow, I confused myself here. So I actually took the moment. Now this is basically because of experience, and if you're thinking ahead, like I must have been thinking ahead a step or two into the future, these two bubbles are definitely going to be needed multiplied together. So all I did here was FOIL these two bubbles together, okay, to get x squared minus 9. And now I'm going to convert. So 2 to the 4th power equals x squared minus 9. And in order to solve this guy, we need to, well, first 2 to the 4th power is 16. And then all I think I'm going to do is, well, here's one way to go about it. Setting equal to 0. And after we set equal to 0, we factor. And after we factor, we set the factors equal to 0. And then we solve each one separately. And just a final reminder that with log equations, there is a potential issue with like the domain and what x is actually allowed to equal. So if I plugged in 5 for x, I would have the log of 8, which is fine. And over here, I would have the log of 2, which is fine. But if I tried plugging in -5, I would get the log of -2, which is not allowed. And, you know, I mean, I could stop right there, but over here I would have the log base 2 of -8, which is also not allowed. So this is actually not an answer, and the only answer is +5. Nope. Happens all the darn time. So that's that.